In this video, I am going to show you how a Pelton turbine converts hydraulic energy to mechanical energy. Now, I want to inform you that I prepared this PowerPoint presentation in the form of a project by organizing many relevant issues from various documents and reports to strengthen the awareness of the students and those who need to know how the Pelton turbines converts hydraulic energy to mechanical energy. So you have to recognize this discussion as an example and a guide to do the real project or research on the hydroelectric power plants. 1.1 Hydropower project. This hydropower project is compressed earth and rock fill dam, intake structure, waterways or address tunnels, vertical pressure shaft, 4 steel-lined penstocks, and 4 terrace tunnels, an overground powerhouse containing 4 Pelton or impulse type turbines and outlet works. 1.1.1 Dam and water conveyance structure. This is very important topic. This hydroelectric power plant operates by the help of different hydraulic, mechanical, and electronic equipments. Those equipments are checked and inspected by the skilled technicians for their correct operation. This is employed by visual inspection from electrical measure or hydraulic flow meters, temperature measurements, if any leakage from oil samples or pipe, so that it is simple to examine the status of station components by observation of their performance. Storage reservoir. This is also very relevant topic. Now I am going to discuss dam and storage reservoir. Storage reservoir, its main purpose is to store water during excess flow period, that means rainy season, and supply the same during low flow periods, that means dry season, and thus it helps in supplying water to the turbines according to the load on the power plant. A reservoir can be either natural or artificial. A natural reservoir is a lake in high mountains, and an artificial reservoir is made by constructing a dam across the river. Now I want to discuss dam. A dam is the most expensive and important part of a hydropower plant. Dams are built of concrete or stone masonry, earth or rock fill. The type and arrangement depend upon the topography of the site. A masonry dam may be built in a narrow canal. An earth dam may be best suited for a wide village. In this hydroelectric power plant, an earth and rock fill dam is used. It is a curved dam and transmits a major portion of its water pressure horizontally to the abutments by arc action. It is 22.2 meters high, 340 meters wide, and has an inherent stability against sliding. The function of dam is not only to raise the water surface of the stream to create an artificial edge, but also to provide the bondage, storage, or the facility of diversion into conduits. Thus, earth and a rock fill dam are formed of loose rocks and boulder filled in the riverbed. A slab of reinforced concrete is often laid across the upstream face of a rockfill dam to make it watertight. This is also the most crucial topic in this presentation. Criteria for safe design of earth dam. An earth dam must be safe and stable during phases of construction and operation of the reservoir. The practical criteria for the design of earth dams may be stated probably as follows: no overtopping during occurrence of the inflow, design flood. Under these issues, we have to consider appropriate design flood, adequate spillway, sufficient outlet arcs, sufficient freeboards, and no seepage failure, and we have to consider no structural failure, foundation shear stress within the safe limits, earthquake resistance dam, proper slope protection against wind and raindrop erosion, proper drainage and economic section. Water conveyance structures. Water conveyance structure include intake, spillway, gate chamber, trash rack, high pressure tunnel, surge tank, valve chamber, penstock, inlet valve, and a draft tube. As you can see, this is a flow diagram of hydropower system components. Now I want to discuss these important terms one by one. First, I am going to discuss intake. Intake is a structure that is constructed to divert the required amount of water from the source such as reservoir or river into power canal or into a penstock that conveys the water to a powerhouse without producing a negative impact on the local environment and with minimum possible air loss. Intakes are usually provided at the entrance of a power canal or penstock. As you can see, this is a figure of tower intake of hydroelectric power plant. This tower intake is contain trash rack, curtain hall, bulk air gate, different gates, transition, air inlet, bridge, hoist room, hoist, and other several devices. 1.2.2 The main functions of intake. To control flow of water into the conveyance system, the control is achieved by a gate or a valve. To provide smooth, easy, and vortex or turbulence-free entry of water in the conveyance system, this is to minimize air loss. This can be achieved through providing bell-mouse-shaped entrance. To prevent entry of coarse, river-borne trash matter such as boulders, logs, tree branches, extra provisions of trash rack at the entrance achieve this function. To exclude heavy sediment load of the river from entering the conveyance system, special devices such as silty traps, silty excluders are used to control and trap the silty. Intakes are conveniently classified into the following types depending on the power plant type and it is layout: runoff river intake, canal intakes, dam intakes, tower intakes, shaft intakes. This hydropower plant comprises the power intake with tower type on dam at the left bank. it has an invert elevation of 2,212 meter. Tower intake used when it is not convenient to provide the simple intake directly on the upstream face of the dam. Also used when these are wide fluctuation in water level. Tower may be connected with main dam through a bridge when the tower is near the dam. Flow into the tower is controlled by a number of gates to control or open the ports at various levels. Flow through the pressure conduit is controlled by vertical uplift gates. The structure should be strong enough to withstand aerodynamic, earthquake, wind, etc. The tower intake will have the following components: trash rack and skimmers. The trash rack is made up of one or more panels, each generally fabricated of a series of evenly spaced vertical metal bars. A trash rack intercepts the entry flow and remove any large debris, whether it is floating, suspended, or swept along the bottom. A skimmer hole is an obstruction placed at the water surface, usually at an angle to the stream flow, which skims floating debris from the passing water. If the water level changes markedly, as for example at the intake of stream, the skimmers can be floating piece of timber secured at both ends. If changes in water level are small, a fixed skimmers because some of the words usually passes under the skimmers. A trash rack is still necessary. However, a skimmer reduces the frequency with which the trash rack has to be cleaned. This is the next topic. A spillway. A spillway is an outlet from a reservoir or section of a dam designed to release surplus fluid that cannot be stored for generating power. The essential requirements of a spillway are: the spillway must have sufficient capacity. It must be hydraulically and structurally adequate. It must be so located that it provides safe disposal of water. That means spillway discharge will not erode or undermine the downstream of the dam. The bounding surface of spillway must be erosion resistant to withstand the high scoring velocities created by the drop from the reservoir surface to the tear water. There are several spillway types. The choice of type is a function of the nature of the site, the types of dam, and the overall economics of the scheme. Generally, the required capacity of spillway depends on the flowing factor, inflow rate, available storage capacity, discharge capacity of outlet works, whether gated or ungated spillway, possible damage if a spillway of adequate capacity is not provided. Based on prominent features or according to hydraulic criteria, a spillway can be classified as overflow or ogee spillway, side channel spillway, siphon spillway, free overflow or straight drop spillway, shaft or morning glory spillway, conduit or tunnel spillway. Most of the time, for hydro power plant project, overflow or ogee spillway is selected on the embankment dam. 1.3.1 Gate chamber. It is one of the structural parts of this project or Rockfield Dam. When the hydro power plant stops by any case, then The outlet water stops during this time. The irrigated land gets wetter by opening the gate chamber. High pressure tunnels. Tunnels are underground conveyance structures constructed by special tunneling methods without distributing the natural surface of the ground. In the areas of water conveyance system, tunneling is popular because of the flowing reasons. It provides a direct and a short route for the water passage, thus resulting in considerable saving in cost. Tunneling work can be started simultaneously at many points, thus leading to quicker completion. Natural landscape is not disturbed. Tunneling work has become easier with development techniques of drilling and blasting and new mechanical equipment. Development of rock mechanics and experimental X-rays analysis has given greater confidence to engineers regarding the stability of tunnels. Tunnels of hydropower project fall into two categories: water carrying tunnels and service tunnels. When it comes to water carrying tunnels, these include head race or power tunnels, tail race tunnels or diversion tunnels. Head race tunnels are tunnels that convey water to the surge tank. These are pressure tunnels. Service tunnels, these may be cable tunnels, ventilation tunnels, HASIS or approach tunnels. Cable tunnels to carry cables from underground powerhouse to the switch yard. Ventilation tunnels fitted with fans at the open end to supply fresh air to the underground. ACES or approach tunnels. This is a passage tunnel from surface to underground powerhouse. Surge tank. The surge tank, also called the expansion chamber. This hydropower plant surge tank has the following characteristics. It has 7-meter diameter, 50-meter height, 3-kilometer distance from the dam. As you can see, this picture is surge tank. Surge tank. The surge tank serves the following purpose. It provides a free reservoir service close to the discharge regulation mechanism. This will cut short and limit the conduit length liable to water hammer. The force resulting from changing the speed of the water mass causes a pressure rise in the pipe with a magnitude several times greater than the normal static pressure in the pipe. This phenomenon is commonly known as water hammer. It supplies the additional water required by the turbine during load demand or during starting up until the conduit velocity is accelerated to the final steady state level. It stores water during load rejection until the conduit velocity is decelerated to the new steady state condition. It assures that the water level oscillation following small and large load changes are dissipated rapidly. Types of surge tank. Surge tank may be classified according to material of construction, example, concrete or steel. Location relative to terrain. Underground surge tank, that means excavated surge tank. Overground surge tank or freestanding surge tank. Location in the hydraulic system, upstream surge tank or upstream to the powerhouse on the address tunnel. downstream charge tank on the terrace tunnel, hydraulic functioning, and cross-sectional shape. The most useful classification is on the basis of their shape, which also determines their hydraulic characteristic. Usually, fluid classification is as follows: simple surge tanks, restricted orifice surge tanks, differential surge tanks with expansion chambers, and others. Valve chamber. A shut-off valve may be required at the powerhouse end of penstocks for either turbine or pump turbine units. The purpose of these valves is to provide emergency shut-off in case of flooding, type failure, or loss of speed control, reduction of leakage through needle, and for maintenance of the turbine. Several factors should be considered when deciding the need for a shut-off valve at the unit. The factors include but are not the following: types of shut-off at the penstock intake, length of penstock, head, multiple units per penstocks. This extraordinary figure is valve chamber of hydroelectric power plant. As you can see, it has several valves. 1.4 penstock. The penstock is high pressure pipeline between surge tank and reservoirs to turbine. Factors that must be considered for choice of material for pressure tunnels are head, topography, discharge. This hydropower plant penstock consists of the following characteristics: 2.1 meter diameter, 558 meter underground, buried penstock, 1359 meter exposed on Earth's surface. As you can see, this picture is penstock provided surrounding powerhouse. 1.5 preliminary power assessment and powerhouse layout. Before any power plant is contemplated, it is essential to assess the inherent power available from the discharge of the river and the aid available at the site. Let P is the power potential of the river. P is equal to efficiency times species width times discharge times aid. The gross aid is the vertical distance that the water falls through the generating power that is between normal pole level and the terrace level. Gross aid is calculated by using this formula, or gross aid is equal to normal pole level minus tail water level. Net aid is the gross aid minus the sum of all the losses arising from trash racks, pipe friction, bendings, and valves. The net aid is the available aid to drive turbines. The total net losses are given by net aid is equal to gross aid minus aid due to friction loss. Layout of hydropower project. The hydroelectric deployment ordinarily includes diversion structures or dam, weir or barrage, conduit or penstock or a channel to carry water to the turbines, and a governing mechanism, generators, control, and switching apparatus. housing for the equipment, transformer and the transmission lines to the distribution centers. In addition, trash racks at entrance to the conduits, channels, and the penstock gates, a forebay or surge tank, and other appurtenances may be required. Firm power in the installed capacity. Firm power. This is the minimum continuous power that is available for the plant under the orostic hydraulic conditions. Installed capacity. This is the total capacity of all the turbine generator units in the power station. For the preliminary design, it is obtained by calculating the maximum power that can be supplied from the power plant at the highest regulated water level in the intake. Installed capacity. Installed capacity is calculated by using this formula. If you take 34 megawatt for 1 unit, we can calculate installed capacity for 4 turbine. Total power will be 4 times 34. Then it is 136 megawatts. Simply, we can estimate installed capacity by using this formula. 1.6 Types of powerhouse. Power station can be classified as surface power stations and underground power stations. Surface power station. A surface hydropower station structure can conveniently consist of 3 main divisions: the substructure, the intermediate structure, the superstructure. As you can see, this is superstructure of powerhouse. Surface power station. The substructure, it is situated below the turbine level. In case of reaction turbines, it consists of draft tubes, whereas in Pelton turbines, it consists of the terrace channel. It also transmits the loads of the structure above it to the foundation strata and is usually consists massive concrete. The intermediate structure extends from the top of substructure to the top of generator foundation in vertical layouts. It accommodates the hind pieces of the penstock, valves, scroll case, and a runner in reaction turbines, and the distributors, nozzles, and runners in Pelton turbines. The superstructure accommodates the generator in vertical and horizontal shafted layout, oil pressure governing system, control cubicle, and the overhead reaction cranes. Underground power station. The powerhouse is located below the natural ground level with the pressure tunnel, penstock, main powerhouse cover, and a tape raise tunnel. Such powerhouse can be provided only if stable geological strata are available at the powerhouse site. Valves. Valves are controlling structure installed at 2 places where the flow is to be regulated and controlled. The main purpose of penstock inlet valve is for dewatering of the penstock in case maintenance of the penstock is required. The main purpose of turbine inlet valve is to close the penstock while the turbine is inoperative. It can also act as an emergency shut-off device. There are various types of valves for use in hydropower installations. The most frequently applied include gate valves, butterfly valves, spherical valves, and needle valves. This figure is indicates that inlet valve of hydroelectric power plant bypass, a bypass valve permitting equalized pressure on both sides of the spherical valves before opening should be provided. The bypass is normally motor operated for automatic control. As you can see, this is bypass of hydroelectric power plant. 2.1 Hydraulic turbine. Hydraulic turbine is a machine which converts pressure of kinetic energy of water into mechanical energy. Turbines basically fall into two categories: reaction turbine and impulse turbine. Reaction turbines, in these types of turbine, the water enters the turbine in circumferential direction into the scroll case and moves into the runner through a series guide vanes called wicket gates. Some examples of reaction turbines are, for instance, Kaplan, propeller, valve, etc. Impulse turbine, all the available potential energy is converted into kinetic energy with the help of contracting nozzles. Example for these types of turbine is Pelton wheel. This is a picture of turbine of hydroelectric power plant. The structure of the turbine. The turbine consists of rotating parts, embedded parts, servo motor, air admission system, instrument, pipeline, and tools. Rotating parts contain runners, main shaft, shaft gland, turbine guide bearing. Now I am going to discuss these terms one by one. Runner. The function of the runner is to convert the potential energy of pressure or aid and a flow of water into mechanical energy or rotational horsepower, which is supplied directly to the turbine shaft. Main shaft. The function of the turbine shaft is to transfer torque from the turbine runner to generator shaft and generator rotor. Shaft gland. The shaft gland is radial mechanical type, which consists of main shaft segment, main shaft seal, press, plate, and spring. The shaft seal prevents water leakage between main shaft and air cover. This is runners, runner of parts of Pelton turbines. 2.1.3 Turbine guide bearing. The function of the turbine guide bearing is to resist the mechanical imbalance and hydraulic side loads from the turbine runner, thereby maintaining the turbine runner in its centered position in the runner seals. As you can see, this turbine guide bearing as lower guide bearing, upper guide bearing, and turbine guide bearing. Embedded parts consists of the steering, spiral case, draft tube, page, linear, bead liner, floor, and railing. The steering could bear the distributor, guide bearing, and parts of generator. The spiral case steven used to lead the water into the runner and make the runner rotate. Stay ring. The function of the stevens and steering is to align the flow of water from the spiral casing to the wicket gates. Spiral case. The function of the spiral case or scroll case is to supply water from the penstock to the stay vanes and through its unique shape of continual cross-sectional area reduction, maintain a near uniform velocity of water around the stay vanes and wicket gates. Spiral case. This is a picture of spiral case of turbine. As you can see, it has needles, nozzle, and many remote control devices. Wicket gates. The function of wicket gates is to control the quantity of water entering the turbine runner, thereby controlling power output. The wicket gates also function as a closure valve to minimize leakage through the turbine while it is shut down. Guide vane is used to transmit the water from the spiral case steering to the runner so as to make the runner rotate. The guide vane opening is controlled by servo motor. The operating ring and the gate linkage. The ultimate aim is to adjust the output through varying the water discharge capacity. Servo motor is to be operated with oil which is transported from the governor via pipes. It makes the operating ring rotate through the guide vane operating mechanical mechanism, making the guide vane rotating. Each turbine has two pressure-operated double-acting guide vane servo motors. Generator. It is used to convert mechanical energy to electrical energy. Structure features of generator is stator, rotor, thrust bearing, stator. The stator frame is a welded construction designed for high torsion, buckling, and vibration stiffness. The stator frame rests on sole plates embedded in the concrete foundation. Rotor. The rotor is designed as a radial ventilated laminated rim consists of steel plates stacked on sides. Rotor consists of poles and a spider. Thrust bearing. As you can see, this is the figure of turbine and a generator of hydroelectric power plant. As you can see, there's rotor, stator, generator, turbine, generator shaft, and a terrace. Cooling system. The preferred option for engine cooling, water heat rejection, an exhaust for removing air heated by engine surface, and a generator exciter. As you can see, this is a figure of cooling pump and a cooling system of hydroelectric power plant. Cooling system. These systems are installed for two types of oil, governor lubrication oil or governor lube, and insulating oil are required in most powerhouses. The systems are based on the use of common oil for unit lubrication and governance systems and for transformers and circuit breakers. Oil system. These systems are installed for two types of oil, governor lubrication oil, governor lube, and insulating oil are required in most powerhouses. The systems are based on the use of common oil for unit lubrication and governance systems and for transformer and circuit breaker. Governor. In order to have electrical output of constant frequency, it is necessary to maintain the speed of the alternator driven by the turbine constant. This is achieved by controlling the flow of water entering the turbine by the automatic adjustment of guide vanes. Such an operation of speed regulation is called the governing, and it is attained automatically by means of the governor. For this electric power plant, governor cabinet is located on the generator floor. Governor system components. The first one is electronic digital governor. Electronic turbine speed governor basically maintains the same turbine speed at any unit load. Governor also operates inject and deflector in the different manner at a turbine start and stop. The main governor function unit are governor speed measurement, ID regulator with water hammer compensating function, power control loop, opening limiter, positioning loops for hitch, injector, and deflector servo motor. The second one is governor oil pressure unit. Pressure oil used for governing and the control functions of the system is taken from oil pressure unit. The pressure accumulator is used for pressure energy accumulation. Pressure oil used for spherical valve control. The separate system is provided. The oil pump operates intermittent like the pumps in governor system. The third one is devices for turbine protection. Devices for turbine protection perform the unit shutdown in the case when turbine or generator protection is activated. The fourth types of governor system components is hydraulic governor. The governor hydraulic system is servo mechanism composed of variety of electrical and hydraulic components. In the hydraulic system, the control oil and operating oil are independent to assure the system operations safety and reliability. The operating oil is provided through main distribution valve from oil pressure unit to gate servo motor, and the control oil is also from oil pressure unit, and it is transported to the hydraulic system control part after filter. This cool picture is indicated that injectors and deflector hydraulic control governor systems. (2.6) Outlet structure, that means draft tube and the terrace. Draft tube, the function of a draft tube is to gradually slow down the high discharge velocity water, capturing the kinetic energy from the water, which is usually below atmospheric pressure. Terrace, the outlet structure comprises 4 terrace tunnels to discharge water back to the river from the turbines after power generation. Stop logs of hydroelectric power plant which can close the water flow to the turbine. Stop log are hydraulic and engineering control elements that are used in flood gates to adjust the water level or flow rate in a river canal or reservoir. Stop logs are designed to cut off or stop flow through a conduit. All these decisions shows that how Pelton turbines converts hydraulic energy to mechanical energies. Thank you for your attention.